Yeah, thank you very much. So I already gave this talk in autumn in Mexico, but maybe only Dima was there, so I think it's okay to talk about this. The goal of the talk is to make a review of conjectures that relates Hodge numbers, or maybe even Hodge structures of dual mirror symmetry dual objects. And so I'll start from some mirror symmetry consideration and finish with when I'll talk about sketch of some proofs. I'll finish with actually very elementary aberrational geometry. The motivation of these conjectures are the following. So from the very beginning, mirror symmetry started from observation that if we have Calabi-Yau threefold, say X, there should exist Calabi-Yau threefold Y, whose Hodge diamonds are obtained one from each other by rotating by 90 degrees. So H PQ of X is equal to H3 minus P Q of Y. So that was the sort of one of initial observations in mirror symmetry, which then developed, we would like to consider this type of relations, but in more generality. So, of course, we can replace threefold by n-fold, just replacing 3 by n here. But we're interested in not only in Calabi-Yau varieties, but for Fano varieties. So mirror symmetry relates Fano varieties. So if X, so everything is smooth over C. As usual. So if F is smooth Fano, then it's dual object, so n-dimensional. Its dual object is not a variety again, like for Calabi-Yau case, but so-called Landau-Giesecke model. So some variety with functions of potential mapping to, so I think we'll denote it by W, satisfying some certain conditions. And if we want to imitate some relations like this for the Fano variety, it's okay. We have Hodge numbers of Fano varieties, but having this family of varieties instead of usual variety, we need to define what means Hodge numbers of this family. So, and this is what Katzarkov-Kontsevich-Pantev conjectures are about. So let me first say some words. What do we assume? Some conditions on Y, and then I'll give some motivation and give you the definition of Hodge numbers, and from which Katzarkov-Kontsevich-Pantev conjectures will be clear. So the objects, by definition, given by Katzarkov-Kontsevich-Pantev, actually there is a very close definition which we discuss in the second part of the talk. But let me start from this. The objects are pairs of smooth compact variety Z with function f, and it's called tame compactified Landau-Giesecke model if the following conditions are satisfied. So first, as I told, Z is smooth. So originally in the Katzarkov-Kontsevich-Pantev assumed that Z is projective, but I don't think so. We should do this because there are examples of non-projective compactified Landau-Giesecke models, but almost projective, so very close to projective. I'll say precisely what is it, and F is F just flat morphism, and the second condition is saying that fiber, so denoted by dz, the fiber, so F, the fiber over infinity, and we assume that so usually it's reducible, but we assume that it's normal crossing. So in particular, it's reduced, which we will use later. And anticanonical class of Z is just a fiber, so is dz, or any other fiber. So anticanonical class of the of this family is just a fiber, and it, so which means that generic fiber over some generic point is a smooth Calabi-Yau variety by adjunction. So, and Landau-Ginzburg model, just not compactified, Landau-Ginzburg model, so which correspond to X, our Y, is just obtaining by throwing away this fiber over infinity. So Y W to C is just Z minus dz, and W is just F restricted to Y. Okay, so motivation of so I'll give two definitions of this dual Hodge numbers for Landau-Ginzburg models, and of course one of conjectures is that these definitions coincide, which is partially proven. I'll tell about this later. But let me start from some motivation of the definition. The motivation, so this definition is inspired by homological mirror symmetry, or part of homological mirror symmetry. So, so it's P1. So F from Z to P1. Yeah, and of course I assume that yeah, so there is no mirror symmetry here, but when we talk about consider these tempo-compactified Landau-Ginzburg models as duals for Fano varieties, we assume, which is not necessary, but we assume that the dimension of Y, so dimension of Y is n. So the same as the dimension of Fano varieties. So that's extra assumption, but in all examples we know, we can find the same dimensional Landau-Ginzburg model. But just now we forget for several minutes about X. We just consider so good family of Calabi-Yau varieties. So one of errors of homological mirror symmetry states that derived category of coherent shifts on our X should be equivalent to Foucault-Seidel, whatever it means, of the dual object, so of dual Landau-Ginzburg model. Well, we are fixing symplectic form here, so it's like a with general symplectic form. But so it's conjecture, of course. But inspired by this conjecture, we can say the following. So if categories are equivalent, then Hochschild homology, the Hochschild homologies should be also isomorphic. So dB of X should be isomorphic. So it's like follows from Hochschild homology of Foucault-Seidel category of YW. But what is Hochschild homology of the right category of X? It's by constant Rosenberg theorem. It's just the sum of cohomologies of forms. So sum of P minus Q is equal to A. HP of omega q of x. So it's classical theorem, and it should be expectation says that Hochschild homology of Foucault-Seidel category is just a relative homology, so n plus a of yb. So b is just a generic point, and so this is yb is a smooth fiber, and so this is a relative cohomology of smooth fiber. So objects of Foucault-Seidel category are vanishing Lagrangians supporting on some smooth fibers. So, and that's why it's a sort of natural to expect that this relative cohomologies should be a Hochschild homology of Foucault-Seidel category. So that's our expectation. This isomorphism is what we need. So if we have two equivalences of categories, then Serre factors should also coincide on both sides. So if Sx is a Serre factor on the derived category, then it's logarithm x here just by multiplication up to a sign by C1 by a canonical class or anti-canonical class. And it determines a filtration which gives us a usual Hodge numbers. So we have a Hodge diamond here. Hochschild homologies are sums of spaces, of vertical spaces, and multiplication by a canonical class or canonical class shifts it so x from here to here, and it's maximally non-degenerate just because the canonical class is ample since our variety is Fana, and it defines Hodge numbers. And here Serre factor or on the Foucault-Seidel category is so it's logarithm by well, it's so it's a operator, so it's linear operator. We can consider a logarithm of just so it's logarithm as x as a linear operator on cohomology, so, and so it stays inside here, so inside vertical things. So so it is just multiplication by canonical class, which or Kähler class in general. Okay, so and here Serre factor x also here, and it's inverse to monodromy. To monodromy operator T. So monodromy acts in a fiber, but considering its trivial action on the whole Y, one can easily define consider monodromy as acting on relative cohomology.
So YB is regular fiber?
Yeah, so it's smooth fiber. So just general fiber is smooth because all Z is smooth, and yeah, and that's relative cohomology. So this means that analogs of Hodge numbers like here should be given by logarithm of this operator, which is inverse to monodromy. So we define by n to be a logarithm of t. Indeed, this classically this logarithm of monodromy defines weight filtration in relative cohomology. So n x on h a or n plus a of y b, So and weight filtration should give dimensions, so should give numbers which should correspond to Hodge numbers here. So this filtration given by operator, so powers of this operator is this weight filtration. It's roughly speaking, if we consider Jordan monodromy, matrix of monodromy in Jordan form, then the middle of the filtration defined by this n is generated by centers of these Jordan blocks. So here we have n minus 1 grade, here n plus 1, and so on. So yeah, so what do we use here? So we used the fact that dz, so use that dz is reduced. Indeed, in this case, in this case the monodromy is maximally unipotent. So by Griffiths-Ladman-Grothendieck theorem, we have T minus identity to the dimension of cohomology n plus a plus 1 is equal to 0. So, and from here we get n to n plus a plus 1 is equal to 0, since n is logarithm of monodromy. Here we know that on the Fano side, multiplication by ample class should be maximally non-degenerate, and so we should impose this here. So we should put Fano condition saying that n to n plus a, so one less, is not equal to 0. So it's like saying that multiplying by anti-canonical class, we get just arrive here, not have something, not have 0 before. Sorry? Why? Yeah. So now I want to define these numbers in terms of this one, and we have slightly different definition for a greater than 0 and a less than 0. So it's imitating to say, so here we have that side of Hodge numbers and of Hodge diamond, and that side, and so we consider it separately, but it's a question of signs. N minus here. It should be not greater than n. Why? Yeah, but here we have this length is 2n. So this distance is 2n. Yes. No. Actually, this weight filtration is even it's on length 2n, which and odd sides, so filtration pieces are trivial. So in fact, you should. Yeah. Yeah. Yeah, but n acts So if we have filtration f, so W0, W1, and so on, n goes to WA to WA minus 2. Here. Yeah, maybe. So, yeah, I agree. So maybe. So let's skip it because maybe so. I need to be a bit accurate. Maybe a model should be put. But yeah, you're correct that n to yeah, I agree. But I'm not completely sure we should put model here, but maybe some change in. But the idea is just maximally non-generacy of this. So by definition, so now we define Hodge numbers for this Landau-Ginzburg model. By definition, H, P. So it's a bit ugly definition, but as it is. So it's the dimension of graded component of 2n minus p of this filtration given by n minus a in cohomology, relative cohomology yb, if this a, which is p minus q, is greater or equal than 0. And for the case when a is less than 0, we have more or less the same, but here we should replace by plus, and here we should replace by n minus q for a less than 0. So it depended on which side of Hodge diamond should we are. Okay, so before writing down this Katzarkov-Kontsevich-Pantev conjectures, of course, claiming that this Hodge number, if y is mirror for fan variety x, then it's Hodge. These Hodge numbers are given by rotating. I'll define another more easy, even more easy version of Hodge numbers, calling f. Yeah, dimension of, so if we have in H, in relative cohomology, we have this weight filtration given by just multiplication by a logarithm of monodromy. And there's certain dimension of a certain piece of grading, of choosing just to correspond to Hodge diamond. These dimensions are just these numbers. So it's n, yeah, so it's n minus a. A is the difference between p and q. So a, in these terms, a is this distance. So if we study this one, so this is a. So I don't know, maybe it's not very well visible from there. Yeah. Okay, so other numbers called FPQ of YW, they are related with, so actually they're defined in terms of Z, so of compactification. Of course, when I'm saying monodromy here, I mean monodromy at infinity. So we don't have fiber over infinity. We don't need Z here. But here we define them in terms of compactification, but actually it doesn't depend on the particular compactification over infinity. So first we consider omega p z of log dz, just a sheaf of logarithmic forms, so differential forms, p forms, which can have just simple poles or on components of dz. So if d is local, dz is locally given by z1 zk, then it's defined, it's generated by zi and dz. So dzi and and dzi over zi. So that's just usual classical logarithmic forms, but we can define the subsheaf of them called f adopted forms. So f adopted forms is just forms omega, so logarithmic forms which stays logarithmic after wedging by differential of f. So such that df wedge omega are still omega logarithmic forms, of course p plus 1 log dz. F yeah, so w adopted forms d. No. F. So let me remind that f. So we have z and map f to p1. And y. So w is so y is z without fiber over infinity, and w is just the restriction. So w is f acting on y. This is defined by there are some spectral sequences related with this. So we have two differentials on this for these forms, just wedging by df and usual one, but they give the same cohomology, so which is a theorem of Katzarkov-Kontsevich-Pantev. And so by definition, f pq numbers of y w is the dimension of this logarithmic form. So is the dimension of hp of, so we denoted them by omega p yf yw, hp of omega q of yw. So dimensions of cohomologies of these sheaves. Okay, so conjecture, so Katzarkov-Kontsevich-Pantev give two conjectures. So one of them states that these two definitions, two sets of numbers coincide. So and another one is related to mirror symmetry, as was written, I think, here where erased, or maybe yeah, on the place which I erased. So the first conjecture of this theorem that this fpq doesn't depend on z. If z is is if the fiber over infinity is normal coarosine. So if you compactify it in two different ways, say if you blow up something, but in fact you can't blow up. So we have a statement that the fiber, the anticanonical class should be a fiber. So you don't have much choice, in fact. So you can do flops, but okay. So the first conjecture says that f pq of y yw is equal to h pq of yw. And the second conjecture states that if y is Landau-Ginzburg model for some Fano variety x, whatever it means for x, then f, so they formulated that for f numbers for f pq of yw is equal to just Hodge numbers n minus p q of x. Before discussing how these conjectures look like in dimension 2 and 3, I'll just briefly say that in fact this is this conjecture follows from some statement and is a sort of particular case of the so-called P equal W conjecture for Landau-Ginzburg model, which states, so the idea of this is the following. So consider our Fano variety X and its anticanonical class. Let's consider its anticanonical class as a sum of normal crossing divisors. So d1 plus dk. So smooth. So let it consider a particular divisor in the anticanonical linear system consisting of, say, k components, which is normal crossing. Then one can associate, having its Landau-Ginzburg model, one can associate with each divisor its own potential. So we have y mapped to C to K, called multipotential, given by W1, WK. So K potentials, of course, whose sum is just a usual potential. So if we have a diagonal map to C, then we have our usual W here. Then we can choose a generic flag of linear space. So well, it's not necessarily linear. You can choose maybe. So it's a discussion if you can choose how general flag can you choose. But let us just choose a flag of linear space in this CK. So sorry. It's a sum, so W is just W1 plus WK. So just for instance, if you have P2, if you have its Landau-Ginzburg model usually written like x plus y plus 1 over xy, then if you decompose this curve of degree 3, which is an anticanonical class on P2, into 3 lines, then here will be W1, here W2, here W3. If you choose line and conic, you can choose, say, this sum will be W1, and this sum will be W2. So that's an example how it works for a toric case. Well, it's I mean, it's even in toric case, it's more a bit more difficult, just because here, well, it doesn't matter. Okay, so if we choose a flag in k dimensional in CK, so we choose HK H0, which is just ck, and this is just a point. Then we can define preimages of this flag on y. So just the sum. So this is the map. So the sum of coordinates. And just like here, we have if we have three maps, W1, W2, W3. So this maps to. Then the usual Laurent polynomial x plus y plus 1 over xy is just W1 plus W2 plus W3.
What is H?
So it's just linear spaces. So if we so it's linear flag in CK. Yeah, generic. So yeah, general one. So I'm not sure we can choose anyone, but general at least is okay. So then we have filtration of cohomology on this our Landau-Giesecke model Y, just given by the following. So we have stratification of y0 equals y, where just yi is preimage, so it's w minus 1 of hi. Just we consider fibers over this flag. And then there is a perverse filtration called Leray filtration, Pg plus I minus 1, filtration on cohomology of the fiber of Y. Sorry? It's the sum of. Yeah. So having roughly speaking, have a splitting of anticanonical class into some number of divisors. We have a splitting of its potential into corresponding the same number of parts.
So HI lives in CK.
Yeah. So it's multi W. So I mean W1 WK minus 1. Yeah. So just preimages. Yeah. Thank you. Yeah, just full flag, usual flag of linear. No, general one. Just general. Actually, in fact, you can maybe consider even a flag of smooth subvarieties, but maybe some restrictions should be put. But this works for linear flag anyway. So we can consider filtration of in cohomology of Y. Just given by kernels, so we have flag on Y, just the preimage of the flag on the base, and we can restrict cohomology from Y to each yi. So kernel of Hj of Y to Hj of yi. I here, yeah. So we have filtration on cohomology given by these kernels, and P equal W conjecture. So I will not formulate it exactly, but it states that mixed Hodge structures mixed Hodge structure of X without anti-canonical class, so of X D correspond to this filtration. P filtration. So say if we have K terms here, then we have K level of weight filtration on mixed Hodge structure, and indeed here we have K flag of K variety, so K filtration of length K here. And actually this Katzarkov-Kontsevich-Pantev conjecture follows from some so if we choose if first Z is of Hodge state type, so only PP cohomology of PP Hodge numbers of A of Z is non-trivial, and if we choose just one divisor, one smooth divisor, so K is equal to 1, then we get Katzarkov-Kontsevich-Pantev conjectures. J plus I minus 1. So roughly speaking, KKP follows in good situation from P equal to W, D is equal to D1. Just one smooth divisor. Okay. Yeah, so we have two conjectures. So this one, in fact, the first one is related with the fact that Z of Hodge Tate type. So in this case, so I'll tell about this. So this is a theorem. So if Z is of Hodge Tate type, then this conjecture holds. And the second part, so this P equal W conjecture, which is related with mirror symmetry, deals with the second part, so with coincidence of Hodge numbers. So it's P. It's two filtrations. So weight filtration and this perverse filtration. So how much time do I have just to plan? 20 minutes. Okay. So now I want to shortly, briefly discuss proofs of KKP conjectures in dimension 2 and 3. But before doing this, I should say, so I told here that we have Landau-Ginzburg, Y is Landau-Ginzburg model for X, whatever it means. So because different people has different conditions, different definitions of Landau-Ginzburg model. So I'll say precisely what I mean. So what are Landau-Ginzburg models for me here, and then discuss proofs of conjectures for these Landau-Ginzburg models. I'll say it very briefly because I'm telling this. So I told it a lot of times, and that's not a main point of the talk. Just, but having fun, we define. So the dimension of X is n. Then our Landau-Ginzburg model will be represented by a Laurent polynomial. So by definition. So this is the data. So toric Landau-Ginzburg model for X is just a Laurent polynomial in n variables P. So we can P is a map from C star to n to C, satisfying three conditions. First one, period condition, saying that so roughly speaking, Grom-Witten theory for X coincide with periods for a family given by Laurent polynomial, so for fibers of this map. So I series or G series given as G series from constructing from X, counting one pointed Gromfittin invariance should coincide with periods. And the periods here for these maps, such maps can be computed very easily. So it's just the sum of constant term of P to I, T to I. One can prove that this is the way how to compute periods very easily. Then there should exist Calabi-Yau compactification of this family. I'll say in 1 minute what is it, because it's sort of important for us. And the third condition, it should exist a toric degeneration of X to some toric variety, maybe ugly, but toric, such that fan. So if we draw a fan of this toric variety and consider its fan polytope, so a polytope convex hull of generators of rays of this fan. So fan polytope of T. So it's not a dual polytope, but polytope defined by fan itself, not by its dual. Should be the Newton polytope of T. Like here, if we have P2, then Newton polytope of a fan of P2, which is toric degeneration of itself. It's like this, and this triangle is exactly Newton polytope of this Laurent polynomial. Even maybe I'll require existence of log Calabi-Yau compactification. And this log Calabi-Yau compactification is very similar to the notion of tame compactified Landau-Gnezuk model, which we discussed. And it's just a fiber-wise it's a fiber-wise compactification of this family. So we have C star to N, map P to C, then we compactify it to Y to Y, where Y is smooth and all fibers are compact. So it's fiber-wise compactification. This is Calabi-Yau compactification, and fibers should be Calabi-Yau. And log Calabi-Yau compactification is a compactification over a base. So we have compactification to Z with a map F to P1, which compactification over a base. And the condition is that minus Kz is F minus 1 over infinity. So anticanonical class is a fiber. So we don't require that this fiber over infinity is normal crossing here, but in practice it happens that it always holds. Yeah, Y smooth and Z smooth. Well, general fiber is smooth, but some of them, of course, are not smooth. Like even here, fiber over infinity is very reducible, and so fibers can be smooth, singular, and even reducible. But general fiber is by Bertini smooth. Yeah, so if we require this one, then it's given by a junction formula that fibers are Calabi-Yau. If we don't have Z, we require that well, it's complete intersection, it's Cohen-Macaulay still, so we can define. So fibers are complete intersections, which means that they are Cohen-Macaulay. And then you can no, the T? Z? no, I don't require Z to be projective, but Y is quasi-projective. So in fact, there are examples in theoretical case which was surprise for me that one can't have a projective Landau-Ginzburg model. So it's in codimension 1 if you throw something in codimension 1. In codimension 2, then you get it will be quasi-projective. So it's almost projective, but we don't require this. Okay, so and this so this compactification, log Calabi-Yau compactification of toric Landau-Ginzburg model will be our definition of Landau-Ginzburg model, for which we would like to check this Katzarkov-Kontsevich-Pantev conjectures. And just let me say that in dimension 2 and 3 they are constructed and well studied by myself, collaborators, other people. So all this data, all this data is known. Yeah. So as a corollary of conjecture of existence toric Landau-Ginzburg model is existence of toric degeneration. But in fact, this degeneration is in sort of anticanonical embedding. So it's a question. So the only obvious abstraction for existence of toric degeneration, so which we can choose, is that which we can try to check is the existence of element of anticanonical class, so anticanonical divisor, but for all fanas, so it exists, and it's expected that it should have such anticanonical. But anyway, in a lot of examples, like in dimension 2 and 3, and for convoluted sections, all this picture is known. Okay, so now I have how many minutes? 10. Okay. Yeah. No, I remember. So now I want to say a couple of words how we construct two ways of constructing this Calabi-Yau compactification. One of them, so the first is very straightforward, and just let us have an example x plus y plus 1 over xy. So we have family lambda is equal to this one. So we want to compactify this family. So obvious way is just to multiply on denominator. We have a family of elliptic curves. It has generic curve is smooth, but the total space of the family will have so the fiber over infinity. So there are three singularities in the fiber over infinity, which is given by. So we multiply by denominator and add the homogenize it to. So we add some variable z. So we have lambda x y z is equal to x plus y times xy plus z cubed. Yeah. So we have a family of compact elliptic curves. So fiber over infinity. So if we consider it like lambda 1 is equal to lambda 2. So this hypersurface, it's singular in 3 points lying over infinity. And if we blow up them, we get compactification. Or we can consider it's just like a family of elliptic curves and blow up a base locus of them. And we get a usual picture of Landau-Ginzburg model for P3, compactified one, which is a wheel of 9 curves, or rational curves over infinity. Generic fiber is smooth. elliptic curve, and 3 fibers have ordinary double points. Another way, so that's the first, we see star cubed squared, so okay, to n, embed to projective space, and blow up base locus. So this, of course, we should be lucky for them to be able to do this, to compactify to a family of anticanonical sections in PN. But it can happen. The second one is more is better. We use the fact that, so if we have a toric variety, then it's anticanonical linear system. It's a linear system of Laurent polynomials supported in the polytope, which is dual to our fan polytope. So this means that we can embed C star to n to the dual toric variety if it exists. So it's, if a polytope is, so if so let us assume that the polytope is reflexive, so the dual polytope is integral. We can construct toric variety from it, calling, so it's dual toric variety. And then automatically members of our family will be anticanonical sections of this toric variety. Then we blow up this base locus of this family and get this Calabi-Yau compactification, together with some description of fiber over infinity, which is more or less combinatorially, it's a boundary divisor of this toric variety. So for this case, it's the following. So our dual polytope, dual toric variety is just singular cubic. So we first resolve singular points. So we have embed this to our family to smooth toric variety, then blow up base locus. And base locus will be like when we blow up, so we have again the boundary of this toric divisor is 3 lines with singularities here. And we have just base locus is an intersection of generic fiber with fiber over infinity, but it intersects in non-toric points by construction, and then when we blow up, we get this Calabi-Yau resolution. And the theorem says that so we can do it easily. So we can do it in dimension 2 and in dimension 3. So it's also true. So if